Okay, good morning, everyone. Hope you had a good weekend. First things first, there's a quiz that was due at 9 a.m. today. So I went and looked. Let me see if anyone's done anything else there. So I wanted to show y'all what I see on my end when you upload these quizzes. So it shows, your name, the file, then what time you uploaded it. 2 a.m. Okay. So just wanted to kind of go through this real quick and just point out, I'm not calling out anyone. This is our first assignment. So remember that if we don't go back face to face, which I have not heard anything yet, if we don't, before our first test, at some point we have to take a test online. You're going to need to be able to submit your work to me as a single file, not as multiple files. So for example, like Alec and Aubrey and where else? Roman. So those three students submitted like separate files, I guess, for each page. And what we're trying to do is get it down to one page. So for those students that I called out, it's okay for this quiz. Don't worry about it. But you want to make sure you know how to get all your pictures into one file instead of multiple files. All right, so after class, if you have any questions on that, I can try and help you. A lot of that will depend on, what kind of phone you're using and then what kind of app you want to use to condense it to a single PDF. Any questions about this? We're good?
Okay. Did you get mine?
Ian?
Yeah, because I uploaded it to the Dropbox like the same day that it was assigned.
This is what I see.
Oh, yeah. When I uploaded it, it said that there was an error.
Okay.
Yeah.
Maybe try and resubmit it.
All right, I'll do it.
Yeah. What I would always do is just, if you're using your phone to take pictures, just make sure you save those pictures in case. For a quiz, it's not that big of a deal, but like if we have to do a test, then if for some reason I don't get the files, then at least you have a picture that has a timestamp on it that shows like when you took that picture. Just don't delete them is what I'm saying. Yeah, so Ian, try it again. I'll leave the Dropbox open for you. Any other questions? Anyone else not see their name there that tried to submit something? Okay, let's get down to business. So we have covered the first two sections on our schedule, 3.5 and 3.6. We finished those up last week. So we're supposed to start antiderivatives and then do substitution rule this week. I'm going to try and see if I can get through this a little faster. So at the beginning of class, first day of class, we talked about, what was Cal 1 about? And then we started talking about what Cal 2 is about. And I told you that Cal 2 is really like three separate ideas, not separate, but three main ideas. First idea is antiderivatives. So we want to be able to do the reverse process of taking a derivative. We want to be able to go backwards. And that inherently has lots of issues. Okay, so that's not easy in general to do. So we spent a lot of time trying to figure out how to do antiderivatives. Then we look at the applications of that we can use the antiderivative for, and then we move on to series. All right, so today is our first step into antiderivatives. So I would say everything we've done up to this point is just kind of like, hey, here's some new functions, here's their derivatives, and now we're ready to actually move down the road for Cal 2. All right, so our notes for this 4.7, remember all these notes are in Canvas. 4.7 is called antiderivatives, and we're going to take a look at the first note here. So this is a definition of what an antiderivative is. So let's just pay attention to the notation here. A function capital F is called an antiderivative of little f on the interval I if the derivative of capital F of x is equal to little f of x for all x in the interval. Okay, so what does that mean? It's most of the time we read definitions, it's not clear until you kind of see the example. So as an example, I can say that capital F of X equals, I'm just going to make up one here, equals X squared is an antiderivative of little f of X, which equals 2X. So this is a true statement. Now, why is it a true statement? Well, the definition says that in order to call something capital F an antiderivative, what I would need is that when I take the derivative of that capital F, I better get that little f. Okay, so when I go back and look at this, if I were to take the derivative, right, if I were to take the derivative of capital F of X, we would get 2X. And that's exactly what little f is. So that checks, right? So the thing that's the antiderivative is this function, right? The capital F of X is the antiderivative of the other function, 2X. Now, my first question to you, and I'll ask, let's go with Alec. Is Alec here?
Yes, I'm here.
Okay. Alec, all right, so let me ask you, do you understand this, Alec?
Yes, I do.
Okay, so my question to you is this the only antiderivative of 2X? Is there any other function you could think of, a different capital F of X that would still qualify as being an antiderivative of that guy? So is there another function you can think of that when you take the derivative of it, you get 2X?
I can't think of it right now. I don't think so.
Okay, okay. How about Roman?
X squared plus 1.
X squared plus 1. Okay, so let me write it down, and then let me go back to Alec. What do you think, Alec? If you take the derivative of that, would you get 2X?
Yes.
Yes, right? So basically that plus 1 that Roman put here really doesn't change the fact that the derivative is still 2X, right? Because the derivative of a constant is 0. So with that idea, this does work, right, everyone? This does work. The derivative of that would be 2X.
Yes.
So Alec, let me ask you again. Can you think of another one? If X squared plus 1 works, do you see what we could do, Alec?
Yeah, so we can just say like it could be the same thing like X squared plus 2, I guess.
Yeah, we could do 2, or we could do 5 or -5 or 10 or -10. It really wouldn't matter, would it? They would all still have that same quality that when we take the derivative, we get 2X. And this is actually a big deal because in Cal 1, if I gave you a function and we took the derivative of it, we got a new function, right? But it was a unique function that we got. There was only one answer. But when you start with a function like 2X and you ask someone to find the antiderivative, we're already seeing that there are an infinite number of answers that it could be, right? X squared plus 1, X squared plus 2, X squared plus 3, X squared minus 1, X squared minus 2, X squared plus pi, right? It doesn't matter. As long as we have X squared there and we add to it any constant, then the derivative should still be 2X. So that leads us to what we call our general antiderivative. So X squared plus 1 is an antiderivative. X squared plus 2 is an antiderivative. X squared by itself is an antiderivative. They are all antiderivatives. But the general antiderivative, the general solution, I guess, should be a function capital F of X equals X squared. So we have to have the X squared there in order to get the 2X. But then we're really free to add any constant to that. Now, when I say add a constant, this could be subtraction because you could add -5 and then it would be -5, right? So that constant there can be any fixed real number. And this is what we refer to as the general antiderivative. That all make sense, everyone? So our challenge here is going to be not that I give you a function and I ask you to check that it's an antiderivative. Our challenge is I give you the little f and you provide me the capital F. That's the hard part. Now, we're going to start off with easy problems, but it'll become more difficult as we proceed. All right, so let's go ahead and do that. Let me give you an example. I'm going to give you the little f. Let's just go with x. And then I want you to find the general antiderivative. All right, let's go with Matthew. Matthew?
Yes, sir.
Okay,
Yeah.
Go ahead. The students that I had in Cal 1, we did this all already. And for a lot of you, you probably already did this in Cal 1. So this might be review. If it's not, it's brand new, and it's brand new. I'm going to present it as if you haven't seen it. So with that said, I haven't given anyone any rules yet, any like formulas. So Matthew, what do you think here?
Um,
Can you find me a capital F? So when I take its derivative, I get X.
so just looking at it right now, I don't really know where I would start at.
Okay, so in Cal 1, when you took derivatives of like X to different powers, like if you had X to the N and you were asked to take derivative in Cal 1,
Mhm.
you would do what with that N?
You would bring it down to the front and then
To the
subtract
front.
it.
Subtract 1, right? N minus 1. So if this is the derivative, right? If
Yeah.
little f of x is x, which is really x to the first power, if that's the derivative of something, right?
Mhm.
Then that 1 is what you got when you brought the power down by 1, right?
Yeah,
Which would mean that your capital F of x would have to have x to what power to it?
2.
2. Okay, so I'm going to put that here, everyone, x squared. Now, this is not going to work, right? Because if you take derivative of x squared, right, you get 2x, right? And you don't want 2x, you just want x. So Matthew, any idea how we might be able to resolve that? When the 2 comes out, we don't want it?
Would you make it I forgot how to do it.
Okay, that's fine. Someone want to help?
We put 1/2 in front.
Put a 1/2 in front. Okay, so now look at that, Matthew,
Yeah.
right? You see that?
Yeah,
So
and then you bring it down, it
1/2, yeah, go ahead.
Yeah, then when you bring down the 2, it'll cancel out with the half.
Exactly, right? So now when you take the derivative, this 2 comes out. Remember when we take derivatives, if we have a constant out front in front of a function, when we take the derivative, the constant comes for the ride, right? So when I take derivative of this 1/2, let's go ahead and do it. When I take derivative of this 1/2 will just come for the ride, then times, now I take derivative of x squared. Now we use the power rule from Cal 1. So 2 comes out, x to the 2 minus 1, we subtract 1, right? The
Mhm.
half and the 2 go away, you get the x and then to the first power, which is exactly what we wanted there, right?
Yes.
Okay. Now I want the general antiderivative though. So even though 1/2 x squared works, because I'm looking for the general antiderivative, all we have to do is just say plus c, and that will be the general antiderivative. So for all antiderivatives, okay, for all of them, you're always going to have this plus c, always, all right? Because no matter what you find is like, this isn't real, actually, I've never heard this in calculus before, but this is kind of like that's kind of like the root function, okay? It's like, that's gonna be there no matter what, right? Like when I'm given x to the first power, I have to have 1/2 x squared in order to make it work. The plus c will be added on no matter what. So no matter where we start from, we're going to go back and try and find kind of like this root antiderivative that I need to make this happen. The plus c is just this result that I can always add or subtract a number and it won't make any difference. We all good? Okay, let's do another one. So what if little f of x is equal to 1 over x cubed? This one's going to be harder. So we're trying to find the antiderivative of this, 1 over x cubed. So what might help to start is to rewrite this as x to the -3. That's what 1 over x cubed means, right? And then we're going to try and see if we can't figure out what the capital F of x needs to be. And let's see, Aaron Leva, are you here? Let's see. Oh,
Hello,
let's see.
good morning.
Morning. You following along?
Yes, sir.
Okay. So I want you to think about this kind of like, well, I don't know your background. You may have done this already, but the same concept is this. We know that when you take the derivative of something like x to a power, the power comes out, you subtract 1. So if this is our answer when you take a derivative, can you tell me, Aaron, what the power of x is going to need to be?
To -4.
Okay, so if it started at -4, then when you took the derivative, you would subtract 1, right? But if you subtract 1 from -4, what would you get?
-5.
-5. So that's not going to work.
-2.
-2, right? Good. So everyone see that? If we start with x to the -2, when we bring the power down, subtract 1, -2, take away 1, that'll give us -3. But same thing, Aaron, this isn't going to work because when you do it, the -2 comes out and we don't have a -2 in front, right? We have a 1 in front.
Mhm.
So what could we put in front here, Aaron, to kind of like kill off that -2 and make things work out the way we want?
You'll add a constant of positive n. So -2 times -2 plus -2 times positive. What the heck?
So yeah, I'm trying to figure out how you're thinking through this. Imagine right now, Aaron, that asks you take derivative of this, right?
Right.
The -2 is going to come out, right? Let's go ahead and do it. You have -2 out front, and then you do subtract 1, you have x to the -3. That's what you would get if you took derivative of this, right? But you want this. You don't want this. So you've got to somehow make this -2 disappear. So what would you multiply -2 by in order to turn it into a 1?
-1.
-1, if I multiply by -1, we're going to get 2. Right? What could I divide it by to turn it into a 1?
-1/2.
Okay, that's what I would multiply it by. That's right. -1/2. Now let's see why. That makes sense, Aaron? You bring the -2 out, it hits a -1/2, negative times negative is positive, and half of 2 is 1. So that should create the one that we want out front.
Okay.
Yes, Aaron, you got it or no?
Correct.
Yes, and then we need to do plus C. And that's it. Okay, any questions? We're going to keep going. Let's do one more, and then we're going to try and see if we can't get a formula going here. If little f of x is, let's say, the 5th root of x, can we find the general antiderivative? And William Little is up. Are you here, Will?
Yes.
Okay. So first things first, you recognize that this is a power, x to a power.
Yes.
Okay, so what's the power on that?
Trying to remember. I know it's like 1/5, right?
1/5, exactly, 1/5. All right. So that's what the 5th root of x means. It's x to the 1/5 power. So this is where things get a little tricky, William, because you've got to sit here and think to yourself, okay, I have x here to some power. And when I subtract 1 from it, I need to get 1/5. Right?
Yeah.
So what do you subtract from? What number minus 1 equals 1/5? What number minus 1 equals 1/5? That might
It's
be a
like,
little,
it's like 6/5 or
it's
something.
6/5. It's 6/5. Good. Now, we're gonna have a formula in a second, but that is correct, 6/5. Because if you subtract 1 from 6/5, you get 1/5. If you don't believe that, just do it. 6/5 minus 1, same as 6/5 minus 5/5. And that's 1/5, and that checks. All right. Now, William, we need something out front though, because again, if you take derivative of this, the 6/5 is going to come out and you don't have a 6/5 here. You have a 1. So what do you need out front to kill off the 6/5 and turn it into a 1?
You would need 5/6.
5/6. Basically, it's reciprocal, right?
Yes.
If you put the reciprocal of it out there, then don't forget, add your C. That will give you your antiderivative. So in all of these problems, what we're doing is if we have, now this is important, if we have a little f, right, little f, where that's x to a power, in every single one of these, we're doing the same process, all right? We're trying to figure out what the power on capital F has to be. Then we're thinking about what happens when it comes out front. You know, when we take derivative, we're trying to kill it off. So let's see if we can get a general formula going. And this is what is going to be referred to as the power rule. Oops, power rule for antiderivatives. All right, so if I start off with little f of x equals x to a power, right, whatever it is, in every problem I've given you, it's been x to a power, then capital F of x will have to be, okay, let's see, Adair, you're up. So what can you tell me? What can you tell me about the power on the x here, Adair?
The power on the x.
Mm-hmm.
I'm a little confused by the question.
Okay, so like in these problems, I've given you a little f, right? And we've found the antiderivative by thinking about this x has to be, how is this power related to that power? Go back to this. Right, like
So
on
we
this
sub-
one.
We
Go ahead.
subtract. We subtract 1.
I
every
need,
time.
yeah, so whatever's here, I need to subtract 1 and get n, right?
Yes,
So that means this power has to be what?
-1 or n minus 1.
Okay, so if you did that, n minus 1, then when you take the derivative, you're going to subtract 1 again. And then you'd have n minus 2 here. So it can't be n minus 1. You might be overthinking this.
I think
In this problem, what was the power here? What was the power on the x on that right there? There. What was the power here?
2.
No, the power on the x.
The power on the x right there is 1.
1. Okay, but the antiderivative of it, what's the power? On our answer, what's the power on the x?
It's squared.
Squared, right? So it went up by 1,
Yes.
right? Same with this one. Well, not that one. On this one, the power was -3, but our answer, we added 1 to that, and it's -2.
Oh, so it's +1?
It's +1, yeah. So if this one was 1/5, the antiderivative is going to be 1 more than that. And that's the general pattern, is that no matter what this power is here on the end, our antiderivative will have a power of n plus 1, right?
Mhm.
Okay, good. Now let's see. Ian, are you here?
Yeah.
Okay, Ian. All right, so what about, is this done, Ian? Do we need more? Is this okay?
No, you
Okay.
gotta multiply the front by the reciprocal of n plus 1. So 1
Yeah.
over n plus 1.
Yeah, so what Ian is saying, am I saying Ian right, or is it Ian?
Yeah, it's Ian. It's Ian.
Okay, so what Ian's saying, just like before, this n plus 1, when we take the derivative, whatever this power is, it's going to come out front. And we don't want it to be there. We want to kill it off. So what we do is we multiply it by the reciprocal of n plus 1, which is 1 over n plus 1. And then we always say plus C. And this right here is our power rule. This will work whenever we have our little f being x to a power. This formula will work to give us the antiderivative. We don't even have to really think about it. We just have to like apply the formula. Now it works almost all the time. There's one value of n that it doesn't work for. Can you all tell?
0.
It should work for 0.
Oh no, -1.
-1. So this formula works so long as n is not -1. Now, Ian, why will the formula not work if n is -1? Why doesn't it work?
Because then you'd be divided by 0.
Yeah, so does everyone see if n was -1, right? If that n right there was -1, you'd have -1 plus 1, that's 0. 1 divided by 0 is undefined. So this formula is only good when the power on x is something other than -1. So that begs the question, what happens if it is, right? So what happens if you do have f of x equals x to the -1 power, then what's the antiderivative, right? Because the formula fails, right? So let's see, Jimmy, are you here? Jimmy, I see you there. Can't hear you, but I see you.
Hello? Okay, I couldn't unmute myself. Can you hear me?
Yeah, no, it's cool. All right, so Jimmy, I'm going to ask you, I'm trying to figure out if you can tell me what the antiderivative of x to the -1 is, but I'm going to help you by rewriting what x to the -1 is. It's 1 over x, right? That's just property of exponents, Jimmy?
Yes.
Now, do you recognize from Cal 1 that 1 over x is the derivative of something? This is something that you should have learned. You may not remember it. It's okay if you don't, but do you recognize that as being the derivative of something?
I do recognize it. I
Okay.
can't recall right now. I have it written down.
Okay.
'Cause I took notes like yesterday, but
Yeah.
I
Okay.
don't know where I put it.
All right. Somebody else recognize it? How about Maria? Is Maria here? Maria. I don't see Maria. Javier?
I can't recall the
No?
answer for that as well.
Okay, let's see how many students we get through before somebody
sir.
recalls. Yes,
Is it a natural log of x?
it's natural log. Okay, good. So that's something you have to recall from Cal 1, that the derivative of the natural log of x is 1 over x. That means that the antiderivative of this is natural log of x and then plus c. So this is the first time, okay, this is the first time in what we've done today. This is the first time that the only way to get the answer is to recall this from Cal 1, all right? Which means you need to know the derivatives of common things, like the important functions from Cal 1. The more you can recall, the easier it will be to find antiderivatives. So now what we have is a general power rule, okay? We should be able to handle any function that has x to a power. We should be able to handle it with our formula or with this natural log. So a lot of the times, this is the way you'll see the formula. It'll say something like this: if f of x, little f of x, is x to the n, it'll say then capital F of x is going to be equal to, and they give you two choices. It's either going to be 1 over n plus 1, x to the n plus 1, plus c. This is what happens if the n is not equal to -1. And it's natural log of x plus c if the n is equal to -1. And so basically this right here covers all possible powers of x. You can find antiderivatives. There's one more thing here. When you do an antiderivative, when you have n is -1 and you get natural log, we will always put the natural log of the absolute value of x. And that is because there's domain issues with natural log. You can't plug in negative numbers. and you can't plug in 0. So we put absolute value so that the antiderivative is actually valid for all values of x within the domain of the original function. Okay. All right, so here's what we're gonna do. I'm gonna give you a couple of problems and I want you to apply the power rules. I'm gonna put you in groups. We're only gonna take maybe 10 minutes for this. Talk to each other. Some of you already know how to do this, okay? But please, help each other out. The problems that I want you to do, first one is gonna be little f of x equals, let's do 3 over the square root of x. Number 2, let's go little f of x equals negative 4x to the negative 3. And the third one, let's go little f of x equals negative 7 times the 5th root of x to the 3rd. Okay, find me, for all of these, I want you to find the general anti, all right? Yeah, 9 minutes. Let's go. Breakout rooms. Once you write them down. There we go. Breakout rooms. It's going to be like 3 to 4 of you in each one. There you go. Okay, everyone should be back now. Okay, so what I've done is I've put the answers here. One of the big ideas I wanted you all to be able to handle was the fact that I threw some constants in here. And you just making sure you understand how to deal with constants when they're out there in front of the function. You just bring them with you, and then just use the power rule on the part of the problem that has x to the power. So I rewrote this one, got this, and then I'm bringing the 3 with me, and then just using the power rule on this. Same thing on this next one. I'm just doing the power rule here. On the last one, I'm just doing the power rule on that. So those are the 3 answers. I'm not sure how far each group got, but does anybody have any questions on these answers? Need me to go through any of these in more detail? One of the things that you're going to have to be able to do or get kind of fast with is adding 1 to fractions, because it happens a lot in this class. Like for example, on this one, we had 3/5. We had to add 1 to 3/5, and that becomes 8/5. That happens so frequently that you might just kind of practice this. If you can't do it in your head, practice it until you kind of can. Just remember, when you're adding 1, you're always just going to be adding whatever the denominator is. You're just going to add that, like 5/5 is the same as 1. So I'm adding 3/5 and 5/5 together to get 8/5. Are you sure there's no questions on these? Plus C on all of them, right? Okay, so I'm going to do another problem, but I'm going to set it up, but we're not going to do it. Let's say we had a problem like this. Little f of x equals 4 minus x plus x squared plus the square root of x, all divided by x. Okay. So with this particular problem, this is the first time that I've given you something where we see a fraction, like we see a quotient, right? This is something divided by something. Everything up to this point has always been just like a number in front of x to a power, number in front of x to a power, well, this one is a number on top of x to a power, but we can move the x up to the top. So when you see something like this, you cannot just do the antiderivative of each of these. You can't say, oh, what's the antiderivative for x squared, this and that. Can't just do all 5 of those separately. Okay, what you have to do is you have to use the very important fact that there's a single term in the denominator. So before you even start the problem, you're going to rewrite this as 4 over x minus x over x plus x squared over x plus root x over x. You break it up into 4 different terms. Then simplify each one of these. This is 4x to the negative 1 minus 1 plus x to the negative half. All I'm doing there is using properties of exponents. And then at this point, the question is, can you do them individually? Right? That's kind of like, are we allowed to do that? And the answer is yes. And the reason you can do them individually now is because you have a bunch of subtraction and addition between terms. And we learned in Cal 1 that when you're taking a derivative, right? When we're doing derivatives, if you have addition and subtraction, you can just do them one at a time when you take derivative. Well, same thing applies when we go backwards. As long as there's a bunch of terms, right, separated by addition and subtraction, we can do our antiderivatives individually. So I'm going to leave this to you. I'm not going to work through this one. I'm just going to tell you what the answer is. It should be 4 natural log of the absolute value of x minus x plus 1/2 x squared. This one should be plus 2x to the half plus c. So make sure you can do that on your own. One of these, the one I think causes problems sometimes for people is this one. What's the antiderivative of 1? And people will forget because it's almost so easy, it's hard. So the antiderivative of 1 is x, because the derivative of x is 1, right? So the antiderivative of 1 would be x. What would the antiderivative of 5 be?
X.
5x, right? Plus a constant. But so no matter what, if we wanted to, we could create a new rule if we wanted to. We could say if little f of x is equal to some constant, I'm going to call it k, not c, then we know that the antiderivative of this should just be that constant times x plus a constant. So again, as an illustration of that property, if little f of x is equal to, let's say, 10, then the antiderivative is just 10x plus c. Okay, any questions? You just need to practice just to get fast with it, all right? I wanted to show you something visually real quick, just to kind of like reinforce what's going on here, especially that plus c. I want to make sure you understand it. So while you were in your breakout rooms, I went to Desmos and I just threw this together. So this is the graph of x squared, right? That's x squared. Actually, this is x squared plus 4. So what we're looking at right now is f of x equals x squared plus 4. Oh, sorry, capital F. We know that this right here is a particular antiderivative of the function little f of x equals 2x. Okay, so if I gave you little f of x is 2x, here's what its antiderivative could be, right? The plus 4, I could use any plus anything, but I'm using plus 4 here. And so there's the graph of the antiderivative. What I want you to see here is that when we talk about the derivative of capital F being little f, what we mean by that is if you were to go to any point on this graph, okay, go to any point on this graph, x squared plus 4, and you were to draw the tangent line, right? I'm just going to go to, hold on, let me make this a little easier. Okay. So let's see, if I go to x squared plus 4 and I go to the point 1, 5, here's the tangent line. You'll see that? That's the tangent line to the curve. So the derivative of this capital F at that point is the slope of that tangent line, right? It's the slope of it. So now I'm going to show you the slope of that tangent line. Which one is it? Hold on. Okay, so I have it calculating the slope of the tangent line. Where did I put it? Yeah, there we go. Okay, so you have to take this on faith, okay? But the slope of this line right now is 2, all right? And that's what this point represents. It means if you go to an x value of 1, the slope there of that purple line will be 2. So if I plot that as a point, there it is. Now watch what happens as I move across the function. I'm going to move this point across the function. I want you to pay attention to this point. Okay, so watch it move. Oh, you know what? I'm going to take that back off. I want it to look a little smoother. Here we go. So watch that point move. You see the red point? See it moving? Okay, if I go to any point on the blue curve and start giving you the slope of tangent line, all those red points get created. And all of those red points lie on a line, okay? So this line here is 2x. That's the graph of 2x. And that's why we say that if you start with x squared plus 4 and you look at its derivative, it's 2x. This red function represents the slope of these purple lines. The whole point of this is this. If I were to move that blue graph up or down, does it have any impact on the slope of its tangent line at points? Doesn't, right? No matter where this blue curve is, the slope of the tangent line there is the same, which is why this red line 2x will always be the derivative of x squared plus any constant. So the moving up and down of the function has no impact on the slope of the tangent lines at every point. Okay, no impact. So if that doesn't make a lot of sense, I can show it to you a slightly different way. Here's the same idea in a different program. All right, there's x squared. Doesn't matter where I move this. Okay, if I take any of these graphs, those are all x squareds moved up and down. No matter where I am on any of these, the slope of the tangent lines are the same. Okay, and that's why you have only one answer. 2x is the derivative. Any questions there? So this idea of a family of functions is an important thing. Anytime you start with a little f and you find its antiderivative, the general antiderivative supplies you with a family of functions. They all have the same shape. They're just like moved, translated vertically up and down, right? That's it. Okay. Now, all we've done so far is looked at the antiderivatives of x to powers. So we should be able to handle x to any power. And if we see something like this example, where you have a bunch of terms over x to a power, you can always split it up. Okay, I want to make sure you understand something. If I were to give you this same problem flipped over like this, and ask you for the antiderivative, you couldn't do it. Okay, you'd be dead in the water right here because there's no way to split that up into multiple terms. Properties of fractions tell you that if you have one term in the bottom, multiple terms on top, then you can split it, but you can't split it the other way around. So here we'd be stuck, all right? In fact, I don't even think we'd ever learn anything in this class that would allow us to find the antiderivative of that. Like there's just no technique that we'll ever learn that'll empower us to do that one, which really kind of should bother you a little bit, because if you were to take all the functions that exist in the universe of functions, right? And you were to say, okay, let's just randomly like reach in there and grab a function. What are the chances that we're going to be able to find the antiderivative using the methods of this class? What are the odds? The probability is actually 0. There's like no chance. If you just randomly just reach in there and grab a function, we can't do it. All right. Which should really bother you, because then you should be saying, well, why are we doing this? Right. Well, there's a couple of reasons why. I mean, a lot of the functions that you do run into in the real world, you can find the antiderivatives of. And even later on, okay, if you grab me a function, even though you may not be able to do it by hand using the methods we learn in this class, once we get to chapter 8 and learn about series, then you can do it. The catch though is that you can do it within a certain tolerance, like within a certain precision. And you can get an answer within a certain precision. So you can't get an exact answer, but you can get an answer that's close enough and close enough to do anything you want to do. So if you want to build a bridge, you come up with some function shows up, you need its antiderivative. Oh shit, I can't do it by hand. Use a series, you can get the answer within a certain precision that's good enough to build the bridge and know it's not going to fall down. I hope that makes sense. It's not like the end of the world that we can't in general find the antiderivatives of things, all right? Because we're saved later by series. So can't do that, okay? Never will be able to do that. So we need to recognize when we can and cannot split things up. Okay, now let me throw a couple of other random functions at you and see if you can come up with the antiderivative, and then we'll think about what we're doing to actually find these answers. So what if little f of x is equal to cosine of x? So let me see. Is it Jaziel? Is it Jaziel, or am I saying that wrong? Jazel? Jaziel? I don't see Jaziel here. That makes it easy. Okay, Hunter, are you here? I see Hunter.
Yes, sir, I'm here.
Okay, Hunter. So what I'm asking you is, do you remember from Cal 1, any function that when you take the derivative of it, you get cosine?
Wasn't I believe it was negative sine x, right? Or I could be wrong about that.
You've got the sine x, right?
Hmm.
The derivative of sine x is cosine of x, right? That's from Cal 1. Derivative of sine is cosine. So that should work, right? But we need to
yes,
do
sir.
plus c, right?
Yes, sir.
Okay, so that was not a rule I gave you, right? Nope, it wasn't a power rule. That's just your knowledge from Cal 1 helping you, right? And we could probably do this for a couple of things we learned in Cal 1. Let's do another one. How about sine x? So can we find the general antiderivative of sine x? Let me ask, I think I've maybe called on everyone in the last few days. I'm gonna go with Aubrey.
So that would be negative cosine x plus c.
Good, negative cosine x plus c. Now, Aubrey put the negative there for a reason, right? That negative is important because back in Cal 1, we know the derivative of cosine of x is negative sine of x, right? So if Aubrey were to have just put cosine, this wouldn't be correct because we would have negative sine x. So Aubrey put a negative in front of the cosine so that when she took the derivative of that and got negative sine, the negative and negative would become a positive, right? So that's important. Make sure you are paying attention to that because a lot of students make that mistake, right? They forget the negative, or they'll do the negative on this one, kind of like, I think Hunter got a little mixed with that. I think Hunter did the derivative of cosine as negative sine instead of thinking of it as a backwards operation, which is very common. Okay, are there any other things I know the derivative of from Cal 1? Hold on. I know that the derivative of tangent, right? The derivative of tangent is what?
Secant x squared.
Secant squared x or secant x squared. Yeah, so I could come up with this. I could say to myself, all right, if I had secant squared x, right? If I had that, then I could tell you for sure that the antiderivative of that would have to be tangent x plus c. And so anything we can think of from Cal 1 that we knew the derivative of, we can go backwards. How about this one? What if little f of x is 1 over 1 plus x squared? What would capital F of x be? So do you remember at any point in your life, being in a math class, that when you took the derivative of something, you got 1 over 1 plus x squared? Do you remember ever seeing that?
Isn't that like the inverse of tangent?
That's yes, exactly. So was it last class? Or the class before? I think it was a class before, maybe. Oh, here. We did it a few times when we worked out the word problem here, but I had highlighted it for you. Remember, I highlighted this and I said, put stars next to it because you're going to see it again. We know from this class, from last week, that when you take the derivative of the inverse tangent function, you get 1 over 1 plus x squared. That means that if little f is 1 over 1 plus x squared, that means that the antiderivative would have to be inverse tangent of x plus c. Let's do another one we should know. How about e to the x?
E to
E
the
to the x.
To the x.
It would be itself. The antiderivative would be itself plus c. And that's just because the derivative of e to the x is itself. So when we take the derivative, we get this. And you know what I forgot to mention? One of the good things about Cal 2 and antiderivatives is that when you get an answer, you can always check it, right? Like you can always check your answers. Like these problems that I gave you to do, you could always go and check, is this answer correct? By just taking its derivative, right? If I take the derivative of this, I better get this. If I take derivative of this, I better get this thing. If I take derivative of this, I better get this thing. So you can always check, you can always know you're right, but you have to be able to take derivatives to do that. So that's good news. We won't do it, but you can do it like on a test or something, check your work. Any questions on this? So where we are right now is this. We're at the very, very like the infancy of this idea of antiderivatives, all right? We're at the very beginning of this. And right now, we should be able to deal with x to any power. We should be able to deal with anything that we recognize from Cal 1, we should be able to do. And then anything else I may have thrown at you in the last week, like this arctangent thing. But that's it. Other than that, we don't have any other way of finding antiderivatives. Understand? So let me throw a problem out here for you. And let's see how this kind of simple looking problem actually becomes somewhat of an issue. All right. So how about this function right here? Little f of x equals, let's go with something like this, cosine of 5x plus 1. So your instinct might be, hey, I know that the derivative of sine gives me cosine, right? So you're kind of recognizing that. So maybe that you go for that and say, okay, capital F of x, maybe it's just, and this is a question, maybe it's just sine of this plus a constant. But that's not going to work, right? So Christian, why is that not going to work?
Because if we were to like take the derivative of that, we would have to do chain rule, which wouldn't end up.
What would you get? Go ahead and do it for me.
Cosine of 5x plus 1 plus 5, or times 5,
right? So you take derivative of sine of something, you get cosine of it, then chain rule says times the derivative of what's inside the argument, and you get 5. And notice we don't have a 5 here, do we? We don't have a 5, not out in front or in the back, right? We don't have a 5. Now, could we insert a 5 to make this work, or sorry, could we kill this 5 off somehow, Christian? We could, right? But it's different. It's different. It's not just sine of 5x plus 1. That's what I'm getting at. It's not as simple as just go back with from cosine to sine. And the reason it's not simple is exactly because of the chain rule. The chain rule causes issues. Let me give you another one. What if I said f of x equals x e to the x squared? So there's a couple of things happening here. First thing you should notice is that this is a product, right? That's a product. So maybe in your mind, you're thinking, oh, you know what I need to do up here? I need to make sure you understand that that's wrong. Okay, that was not correct. So that didn't work. What I'm trying to do is lead us into this next section to show you that things are not as easy as we wish they were. All right, so for this one, I don't know, maybe you're sitting there going, okay, well, look, I got this. Do you know the antiderivative of each of these separately? Do you know them separately? Like, do you know the antiderivative of x? Yeah, right? That's x to a power, so we can use the power rule. Do you know the antiderivative of e to the x squared? I don't know. Do you know the antiderivative of e to the just the x? Like if it was just e to the x, do you know? So I don't know, maybe you're just sitting here first time seeing this, maybe you're thinking to yourself, okay, maybe this is 1/2 x squared, because that's the antiderivative of that, times, and then here, I don't know, maybe it's just itself, because we've learned that the derivative of e to the x is itself. So you sit there and you go, oh, maybe it's this, right? Maybe. Does that make sense where I got that from? Does it seem logical for me to think that maybe that's what it is? It's not, though. How do I know it's not? I just check, right? Check the answer. What's the derivative of this? Well, if I take derivative of this, I'm going to need chain rule, right? I mean, sorry, product rule. I'm going to have to take a product rule. Here's my product right here. So I have to do the derivative of this one first, which the 2 would come out, hit the half, it would go away, just have x times the other function e to the x squared plus, I'm doing the product rule. What is the derivative of e to the x squared? This is tricky. What's that?
Is it 2x e to the x squared?
It's 2x e to the x squared. So that's chain rule, right? The derivative of e to anything is itself, but then you have to multiply times the derivative of x squared, which gives you the 2x. But then you'd have to finish off the product rule. So you then have to multiply by the function that was out front, 1/2 x squared. And when you look at this is nowhere even close to this, right? These are not the same, not equal, right? So that didn't work. So the big challenge in Cal 2 is not how to find the antiderivative of a power of x, or how to find the antiderivative of something you already learned in Cal 1. The challenge in Cal 2 is how do you find antiderivatives of things that have products in them or quotients in them, chain rules involved? Because we already know in Cal 1, product rule makes things complicated, quotient rule makes things complicated, and chain rule makes things complicated. So going backwards from those should be extremely challenging, which it is, all right? So we are, again, stuck, all right? Are there any questions? Like, we don't have any way of doing this cleanly at this point. No questions? Okay. So when it comes to Cal 2, we have what we call techniques of integration, or techniques for antiderivatives, all right? The techniques that we're going to learn, oops. The first thing we learn is the power rule. And, you know, the stuff from Cal 1. That was, you know, we know the antiderivative of cosine and sine, things like that. Okay, we've done this. The next step forward in this class is to learn what's called U-Substitution. Then we're going to learn something called integration by parts. Then we're going to do trig integrals. And don't worry about this, and we'll get to it when we get to it. I'm just kind of laying it out in front of you. And what's called trig sub. And then the last thing we're going to learn is something called partial fractions. We've done this first part, and now we are moving today to try and do this one, U-Substitution. Right, that's what I'm going to continue with here. Now, there's a big thing you need to understand here. All right, this is what distinguishes Cal 1 and Cal 2 from one another as far as the way your brain works. In Cal 1, it's all formulas, right? It's like we give you rules on how to take derivatives. You learn the power rule, you learn the product rule, the quotient rule, chain rule. If you have those rules, you can differentiate anything, right? As long as you understand the rules, you can differentiate anything you want. No matter how complicated it is, you just follow the rules and you're good. With antiderivatives, we do not have a set of rules I'm going to give you that are going to allow you to then find the antiderivative of everything. That's not ever going to be the case. These are what are called techniques. And that word means this is kind of like you're going to have, I'm going to give you like 5 tools in your toolbox, and you're just going to like see a function, try and find the antiderivative, and you're like, look at it and be like, maybe I'll use this tool. That didn't work. Let me try this one. Okay. It's not a process like it was in Cal 1 that like get from point A to point B with a clear path. All right. So you're going to find yourself failing more than you succeed when you're doing this. You're gonna crumble up paper and throw it away and start over a lot. until you get to that point that you're comfortable with the techniques. And then what you want to eventually get to is where you presented with a problem, and then you're like, oh yeah, I know what tool that is. And then you use it and you execute the tool. But that recognition of what tool to use takes time and practice. It's not like the product rule where once you learn it, like you learn it, right? There's nothing, there's like, a monkey could learn it at some point, right? You know what I'm saying? It's just mechanical processes. Executing antiderivatives there's more of like an intuition that has to develop over time. All right, so it's exciting. It's a challenging journey. And we're now like officially putting our toes in the water now, all right? This first thing, power rule, stuff from Cal 1, that's all simple stuff because it's a formula and it's stuff we recognize. U-sub is the first thing where it's like, okay, enjoy, do it, you know, like try it. So you ready to see it? U-sub? Let me bring up my notes on U-sub. Oh, you know what? Yeah, okay, perfect. Yes, yes, yes. Perfect, perfect. Okay, so before we begin, it becomes a real pain in the ass to keep on telling you, hey, go find the general antiderivative, go find the general antiderivative, go find the general antiderivative. So what we do is we adopt some notation, some new notation that will basically let me communicate to you that I want you to find the general antiderivative of a function. And the notation that we use is this right here. Okay, that's this symbol here. It's like an S that's been stretched out, and then f of x. And then next to it, we put dx. That's an important part of this notation. So let me just kind of tell you what each of these things are. First thing, this whole thing together right here is called the indefinite integral. Indefinite integral. Later on, there will be something called a definite integral, but this is the indefinite one. So this is basically telling you, hey, go find me the antiderivative of little f, okay? That symbol out front, that stretched out S, is called the integral sign. F of x, which is the function you're trying to find the antiderivative, is called the integrand. The dx at the end, this piece right here, is called the differential. And we will understand what this means later. Don't worry so much about this at this point. Now, when you do this indefinite integral, you're going to get an answer, right? And that answer is capital F of x. And that is the antiderivative, right? We just talked about that. And then the C that you always have to add here at the end is called the constant of integration. Okay, so this is all just definitions and terminology. So let me give you a quick example here. If I write this down, what's the integrand?
Sine of x squared.
Sine of x squared, right? That's the integrand. So, but at the end of the day, that's just me asking you, hey, can you find me the antiderivative of this, right? Can you find me the antiderivative? That's what that notation means. Questions? The process of finding antiderivatives of functions is called integration. And so Cal 1 is usually referred to, when you take Cal 1, that's usually referred to as differential calculus, meaning you are taking derivatives, right? It's all about derivatives, derivatives, derivatives. So Cal 1 is differential calculus. And Cal 2 is usually called integral calculus because it's all about integration. Integration is the process of finding antiderivatives. And then Cal 3 is usually called vector calculus or multivariable calculus. And what you're doing there is you're taking everything you learned in Cal 1 and Cal 2, and you're applying it to higher dimensional space. So instead of working on flat sheets of paper, you're now moving into 3-dimensional space, 4-dimensional space, 5-dimensional space, and trying to see if you can just translate all this stuff over into those higher dimensions. But that means you need to learn vectors and vector spaces and all that. So there's a lot of like ancillary work that has to be done in Cal 3 to get you going. Okay, so we have already seen the power rule. Okay, so this is just a slightly different notation for what I wrote earlier. If you're trying to find the antiderivative of x to a power, you're going to use this formula so long as n is not equal to -1, and you're going to use this formula if n is equal to -1, right? So we already did that. That's just slightly new notation with this thing out front. And then we have all the common antiderivatives that you should know from Cal 1. Antiderivative of cosine is sine. Antiderivative of secant squared is tangent, right? Antiderivative 1 over 1 plus x squared is inverse tangent. So we've got all that in our toolbox. And now we go about trying to see if we can find antiderivatives of more complicated things. So here's substitution, okay? I have good news and bad news. The good news is that for substitution, it's a very, very kind of like simple set of steps. The problem is that, one, it doesn't always work, okay? It only works if certain things are happening. And number two is that even if this is the correct strategy to work on a problem, you getting to a point where you look at a problem and know this is the correct tool to use is really going to be a challenge. It's easy right now because we know, like right now, I'm about to show you examples using substitution. So when we do them, you know this is what you need to do. But later on a test, I'm not going to present you a problem and say, use substitution. I'm just going to be like, find the antiderivative. And then you have all these tools, and then you're like, which one do I use? So again, the problem recognition is hard. All right, you ready for this? Here we go. So substitution, the general strategy. So imagine that we have here an integral. Okay, just an arbitrary integral. We're sitting there, we're looking at it. Basically, we're being asked to find the antiderivative of something. We've already determined we can't use anything we know, from the previous stuff. It's not something simple, all right? So we look at it, and what we're gonna do is first, we're just gonna look at the integrand, all right? So we're gonna just sit there, we're gonna focus on it, we're gonna look at it, right? We're gonna say, oh, it's this, whatever it is. Now, here's the weird part. What you're gonna do is you're gonna try and find two things within that integrand. And what I mean by two things is two factors. Factors are things that are multiplied together or divided together. So you're going to be looking in here for two different things. The first thing you're going to be looking for is something that I'm going to call something. Okay, this is going to be weird first time we do this, right? So you're going to be looking in that integrand, and you're going to be trying to identify two things in it. The first thing is something, whatever it is, you just say, oh, there it is. And the other factor needs to be the derivative of that something. Okay, so I think it might be worth it for me to give you an example right here. So look at this problem. When you look at this, you need to see the multiplication here. There's multiplication between that x and cosine x squared. And so all the other stuff we've learned will not work for this, all right? We can't use the power rule. It's nothing we recognize from Cal 1. So I'm trying to find something. I'm looking in here. I'm trying to identify something and its derivative. And so what I'm seeing is that x squared could be kind of like my something, right? The thing I'm going to call something. And here, this x right here is the derivative of the something. But there's a problem. Do you all see a problem with that? If I'm saying that the x squared is the something, what is the derivative of this?
2x.
2x. This is just x, right? Not 2x. But I'm still telling you right now that it's okay. I'm going to say that that's the derivative of this. So look at the next line, the next little step. The derivative should appear in the numerator and not be trapped. So do you see this x right here? That is in the numerator, right? There's no fractions here. but you could say that this is in the numerator if it's like all of this divided by 1, right? So it is in the numerator. Do y'all agree? And the other thing is the derivative might be off by a constant, which in this case, is it off by a constant? Y'all told me x squared, right? The derivative of that was what? 2x? We have x, not 2x, right? So we are off by a constant. That's okay. I'm telling you, it's okay. The derivative might be off by a constant, and that's okay. All right, I'm just going to run through that again. You have an integral that's been given to you. You're going to look at the integrand. You're going to try and find something and its derivative separated from one another. The derivative that you see, it can be off by a constant, but it must be in the numerator and it cannot be trapped. What I mean by trapped is it can't be underneath the square root. It can't be within a parenthesis, something raised to a power. It has to be isolated by itself. Now, if all of that looks right to you, like if you've been able to identify something in its derivative off by a constant, not trapped in the numerator, all that crap, if all that crap is good, then you're ready to do the process. The process is now you will let u be the something from part 2. So whatever you said the something was, you're going to replace it with u. And then you go for it. In this step right here, what do I mean by that? Well, we just have to work an example. Okay. All right. Here we go. We are going to do that problem on a separate page. So I would like to know what the antiderivative of x cosine of x squared dx is. Now, I should tell you right now, before we do this, that there are different ways to teach this, present it, attack it. I am presenting it the way, I don't even know if I learned it this way, but this is the way that it makes sense to me, and that's the way I present it to my students, all right? So if you go to a tutor or you've already taken this class and you saw it a slightly different way, I don't care how you do it, as long as you get the right answer and your work makes sense. This is my preference. And so I want to point that out just in case. All right, so I look at this, I identified, here's my something, here's its derivative, I'm off by a constant, I'm ready to go. Okay, so I'm going to do this. I'm going to make a substitution. I'm going to let u be equal to the something, x squared. Now we make substitutions in math all the time. Okay, we've done this back in college algebra. So this is not crazy to say, hey, I'm going to replace x squared with u. The issue, though, is that if this thing becomes a u, all right, think about that. If this becomes a u right here, the rest of the problem has x's, right? This is an x and this has little dx out here. So what we need to do is we need to get everything switched over to u. We can't just pick one thing and make it u and then leave everything else alone. So to get everything else in terms of u, what I'm going to do is take a derivative with respect to x on both sides of this equation. So I'm taking this equation, taking the derivative with respect to x on the left and the derivative with respect to x on the right. That should be just Cal 1. You should be comfortable with that. And then the next part, what I'm going to do is multiply both sides by dx. So I multiply dx on the left, it cancels, dx on the right, it appears. Now that is an important step, because remember the dx in the problem right here? That right there? Do you see that that appears here now? Yes? So we have a way of basically replacing the dx with something, right? Because we have dx over here and it's somehow related to u, right? Okay, next step, here's what I'm going to do. Again, this is the way I like to do it. I'm going to rewrite the problem. I'm going to move the x to the back because it's multiplication. I can always move that x back here. I could always slide that x to the back side. Now, that's why it was important that remember we said look for something in its derivative, but the derivative can't be trapped or in the denominator. This is why, because as long as this x here is in the numerator and not stuck in a bracket or parenthesis or square root or something, we can always slide that to the back, which I've done. And now I'm going to play a matching game. Okay, this is just going to be a game. This x dx I want to replace. I look at this equation on the right hand side and I see I have an x dx, but I don't have a 2, right? There's no 2 here, but there's a 2 here. So I'm just going to do some simple algebra here. I'm going to multiply both sides of that equation by a half. So if I multiply left side and right side by half, I get this. Right, I kill off the 2. And now at this point, I should be able to rewrite the whole problem in terms of u. So I mean, this x squared gets replaced with u. And then this x dx gets replaced with 1/2 du. So let me write that down. Antiderivative cosine of u times 1/2 du. I'm going to rewrite that. I'm going to put 1/2 cosine of u du. Any questions on how any of this happened? We'll need to do more examples, but are there any questions on what I've done here? Okay, then now I want you to just kind of like act like we just started this problem, okay? We just started it, and I presented this problem right here to you. What I'm really asking you to do is give me the antiderivative of 1/2 of cosine of u, right? That's what I'm asking you to do. Well, 1/2 is a number in front, right? So the antiderivative of this should just be 1/2. It comes for the ride. And then you just need to tell me what the antiderivative of cosine of u is, which would be what?
Sine u.
Sine of u, right? But it's sine of u, right? Not x or anything, it's sine of u. So I'm going to put sine of u. That would be the antiderivative. Plus c, though, because we always have to remember to do plus c, right? Again, I can't stress this enough. The integral sign, this thing du, is really asking you to find the antiderivative of this, which is just this, plus some constant. So you see there's no more integral sign. There's no more du because I actually found the antiderivative, right? So this is where I actually did some work, some calculus. Now this is my answer, except for one thing. I have to replace u with what u was. So what was the substitution we had? U was x squared, right? So I'm just going to replace that x squared in here plus c. There we go. Now, if you don't believe that this is the answer, you would take its derivative, right? Just take its derivative, which I'll do real quick. I'm just going to take derivative of that. Okay, if I take 1/2 sine of x squared plus c, if I take that and take its derivative, then the derivative of a constant is going to go away. But this right here, I have to do chain rule. 1/2 comes for the ride. The derivative of sine of something is cosine of it. Times the chain rule, the derivative of the inside is 2x. The half and the 2 cancel, and I'm left with cosine of x squared times x, which is the same as x cosine of x squared, which is exactly what the original problem was. Right? That was the integrand in the original problem. Okay. We have 10 minutes. Let me do another one, all right? Let me do another one. I'll give you a minute to look at it. I'll call on somebody randomly here. I haven't called on, let's see. So if you haven't been called on today, then you're probably going to get called on. So I'll give everyone one more minute. The thing I'm gonna ask is, can you figure out what the U is? Can you figure out what the something is? Okay, I think that's enough time. How about William? William Swope? How's it going, William?
Good. The U would be x cubed plus 2x squared.
Okay, so you're saying the entire denominator, you want that to be your U. And you chose that why?
Because all of the numerator would be the derivative of U.
Yeah, so the derivative of this, right, is 3x squared plus 4x. Right? And that's exactly what we have up top. So if this is our something, right? If this is our something, here's its derivative, right? And also that derivative is in the numerator, right? And it's not trapped. It's not within a set of parentheses or underneath the square root. So this should work, okay? This should work. Does anyone have a question on that? Seeing this something in its derivative?
Yeah, so the derivative has to also be there in the problem for that something to be U.
Yes. Now, when I say it has to be there, I mean, it has to be there. It can be off by a constant though. Right now, it's not off by a constant. It is exactly the derivative of that something, right? If it were off by a constant though, it would still be okay. So it has to be, it could be off by a constant. It could be identical, but it could also be off by a constant. And then it also has to be in the numerator and it cannot be trapped under anything or in a parentheses or a root or something like that. So this should work. So what I'm going to do next is I'm going to rewrite this. Now watch how I rewrite this, and then maybe you'll see why I do this. So I've taken the derivative of the something, right? So the yellow is the something, the derivative of it is the green, and I slid it out to the side like this. You'll see why I did that on the next step, because what I'm going to do now is go over here, take the derivative with respect to x on both sides of this equation. And then I'm going to multiply both sides by dx. And now we just play a matching game. The yellow part here is this, it'll be replaced by U. And then this blue part, which is all of this, matches exactly with all of this, which will be du. So now we rewrite the integral. So Cruz, how are we going to rewrite the integral? Did that sound weird to everybody or just me?
Yeah, his mic
Your
was
audio, you
messed up
sound
in
like a
the
robot.
breakout group earlier.
Try it again, Cruz, one more time. Yeah, something's up with your audio. It's okay. I'll come back to you. I heard you say 1 over u. 1 over u du. Is that what you said? Good. All right. So this becomes 1 over the yellow, but the yellow is u. And then the blue is du. And that's it. Right? That's everything substituted in. So I'm sure Cruz recognizes the antiderivative of 1 over u. Right? That's what we're being asked now. But Brianna will tell us. Because I know Brianna remembers it too, or recognizes it. Bri?
Yeah. It's ln or absolute or natural log.
of the absolute value of U, right?
Yes.
Then plus C.
Plus C.
So again, this is the point where the integral sign goes away. We're actually finding the antiderivative now. So we're just gonna get rid of this integral sign. Remember, all we're doing is looking at the antiderivative of this, which is natural log of U, and then the plus C is because we always have to have the plus C. The final step would be to replace the U with what U is, which is x cubed plus 2x squared plus C. And that should be our antiderivative. You could always check your answer, right? Take the derivative of that, you better get back the original one. Okay, so we're just getting into this, all right? We're just getting into the U-substitution. We're out of time. So what I'd like for you to do for homework is make sure you do all the 4-7 homework, okay? Take care of that. Now, on the substitution rule, I don't want you to do all of it. I only want you to do the first 6 problems. 1 through 6 only, all right? Now, I'll explain, I'm gonna show you in the last minute I have why I'm asking you to do the first 6, all right? Everyone got that, 1 through 6? I'm gonna give you an example of what these problems look like. So they give you like let's say number 3. They give you the integral of x squared, then they give you the square root of x cubed plus 1 dx. And then they tell you U is equal to x cubed plus 1. So in the first 6 problems, they're going to give you what U is. They are going to point out to you what the substitution is. If I were you, what I would do is try and do these problems initially, try and do them without looking at what that is. See if you could come up with it on your own. And then try and do the problem. If you can't, then go ahead and look at what the substitution is. And then hopefully by seeing the substitution being made and converting everything over to U, you'll start to get a feel and flavor for how this works. If you want, you can try the others in the section, especially if you've done substitution before. But there are certain things that we'll run into with substitution that aren't as clean and clear and cut and dry. Sometimes you use substitutions that don't make any sense and they still work. So 1 through 6, you should be able to handle. The rest, at your own risk. We'll come back, we'll do a bunch more substitution, and then we will start integration by parts next class also. Remember, we have a holiday on Monday next week. So we have 2 classes this week. We only have 1 class next week, and then we come back and we have an exam. So we're supposed to, you know how we're supposed to go back on campus? It's actually supposed to happen on September 8th because September 6th is an actual holiday. Has anyone heard anything? Y'all can go if you need to go. Has anyone heard anything about going back? I haven't either.
Will you know by Wednesday?
I have no idea. I don't want to make any sort of promises here. I'm checking my email real quick to see if anything came through while we're in class. I don't see anything.
What's the criteria for them making the decision if we do or don't?
I have no idea. Yeah, I mean, I'm not part of those meetings, and it's a district decision. It's not even a college decision. So it's, all 5 colleges have what do you call it? Board of, not a board, trustees. Yeah, board of trustees. And they work with the chancellor, and then they have some team that's, looking at safety and blah, blah, blah. I mean, I think we all would like to go back. I mean, we all